Welcome back to a new chapter, Chapter 10. Chapter 10 is all about conic sections. And you might be thinking, what is a conic section? Well, that's what we're going to be learning about in this chapter. Today's an introduction to conic sections. And then throughout the chapter, we will look at each one individually and then wrap it up all at the end. On this screen, I actually have all four conic sections that we will be looking at. That's why it looks a bit cluttered. We have a circle, we have an ellipse, we have a hyperbola, which is both of these guys, and then parabolas. You might think, well, I've dealt with parabolas before. We spent a whole chapter 5, on parabolas, and they didn't look like this. They were going up and down. Well, yes and no. We did not look at parabolas in Chapter 5. We looked at quadratic functions in Chapter 5, whose graph does happen to be a parabola, but parabolas are a bigger topic than just quadratics. For instance, they can go sideways and don't have to be functions. In fact, the circle's not a function, the ellipse is not a function, and the hyperbola is also not a function. We really finished with functions last chapter, and now we get to deal with other stuff that's way more fun than just a function. And so, today we're going to be seeing what these things actually are, how we come by them, and why they're called conic sections in the first place. Seems like a weird name for circles, ellipses, hyperbolas, and parabolas, but we'll see why. So, learning targets. I can recognize conic sections as intersections of planes and cones. Sounds kind of weird. That'll be the first thing we look at. And I can use the distance and midpoint formulas to solve problems. And so distance and midpoint formulas are actually just review from geometry, and even before that, you've been dealing with distance and midpoint for quite a while. So we'll get to that at the end. First, though, what are conic sections? So we get conic sections by cutting a cone with a plane. The first cut we're going to make is just a horizontal cut. If we have a cone that's point up, we're going to make a horizontal cut, like this little red cut right here in this cone. Now, what shape does that make? Well, if we rotate where we're looking at it, that gives us a circle. So a horizontal cut in a cone will give us a circle. The next cut we're going to make is one that's angled. We're going to make an angled cut, like this yellow cut right here. And so if we look to see what shape that makes when we can see the plane, that gives us an ellipse. And so here we have an ellipse when we make an angled cut. Now we're going to angle it even further so that it's actually parallel with a side. So if we make that cut, this cut, which is parallel to this side, and we can look, and that's where we get a parabola. And then finally, a vertical cut, and by process of elimination, you can probably figure out this one's going to be a hyperbola, but a vertical cut, straight up and down, we get a hyperbola. Now, I know that hyperbolas and parabolas look a bit similar. They have some pretty key differences in both the definition and how they're made. And when we zoom out from them, parabolas keep curving, whereas hyperbolas are asymptotic. And we'll see that a lot more when we're dealing with them. But if you remember the hyperbola, it was the green one on the front screen that was on the bottom and on the top. There are two parts to a hyperbola. And why would that be? Well, that happens because this is not our cone with the cut in it. This is actually only half of a cone. A cone is defined by taking a straight line. So if we have a straight line and we're going to rotate it, we're going to pivot it about a central axis or central point. And so if we pivot it like that, we can see that this is actually only half a cone. So when we take a vertical slice, we actually cut into both the top and the bottom. None of the other slices, the circle slice only hits one piece. The ellipse slice only hits one piece. The parabola slice, which is parallel to this side, parallel to this line, will only hit one piece. So the only one where we get the two sections is a hyperbola. So if we rotated this, we'd get the two pieces of our hyperbola. Now the book has a pretty good graphic that shows all four of them. And that would be here, and it's right on the front page of this section. But we can see a horizontal cut's a circle, an angled cut's an ellipse, a parabola is more of an angled cut that's parallel to the side, and then a hyperbola is straight up and down. We can see it hits both pieces and gives us a shape like that. And then I have my wooden cone that has all four cuts on it. So you can see the circle cut, the ellipse cut, the parabola cut, and then the hyperbola cut. And that's just because I have the cone. It's one of my cool toys, and I wanted a picture of it to be in the video. This is another one of my cool toys, but I put videos of it in the video. So, there we go. And so that's what conic sections are. And again, we'll be dealing with them. Tomorrow we'll look at circles, and the next day we'll look at ellipses, and then next week, Monday and Tuesday, we'll look at hyperbolas and parabolas. And so, but today, we're going to be looking at graphing conics on a calculator, and then identifying them based on what they look like. So, we'll be given an equation, kind of like 3x squared plus 3y squared equals 48, and we're going to graph it on a calculator. Well, to graph things on a calculator, it has to be y equals something. So, the first thing we need to do is we need to get it to look like y equals something. First step, subtract the other term. 3x squared, subtract over to the other side. Now we have 3y squared equals something. Divide by 3. Now in this case, both of these are divisible by 3. If they weren't, we could have put 48 minus 3x squared all over 3 if we really wanted to. Chances are you're not going to have to do that, but you could if you had to. So now we have y squared equals something. So we're going to square root both sides. Now the square root of 16 minus x squared is not 4 minus x. I will repeat, it is not 4 minus x. It's the square root of 16 minus x squared, and that does not simplify. It is plus or minus, however, because that'll get both the positive piece of it and the negative piece of it. Each of these separately are functions, but this conic section is not going to be a function, and our calculator graphs functions. So the plus or minus will take care of that. So how do you graph a plus or minus? There's two ways. The first way, you just split it into two equations. y1 equals square root of 16 minus x squared. y2 equals negative 16 minus x squared. You graph both of those. So, to do that, get out our graphing calculator, and we're going to graph. We're going to go to y equals, and in y1, we're just going to type square root of 16 minus x squared. Square root of 16 minus x squared. And when you're using x, make sure you use this one. I've caught people trying to use the letter x. That doesn't work out. In the bottom one, negative 16 minus x squared. You could actually do negative y1 if you wanted to, which would be alpha trace to get to y1, but you can just type it in. And we graph it. And hey, this looks like an ellipse. But the thing with the graphs is, notice this x distance is way bigger than that y distance. That's because it's going from negative 10 to 10, negative 10 to 10. So we're going to zoom square, and that is going to make those distances equal. So now we can look, hey, look, this looks like a circle. Notice there's gaps here. That's just the way the calculators handle things. So the gaps shouldn't actually be there, but again, that's something we can't get rid of on the calculator. And then we can look to see our center. Looks like it's centered on 0, 0. And our intercepts, looks like we're at 4, 0, negative 4, 0, and 0, 4, 0, negative 4. So it's a circle, center 0, 0, and we have some intercepts. So that's how we graph a conic section on a calculator. We have to solve for y, and then we can graph with plus or minus. The next one I'll show you how you can, another way of doing the plus or minus. So speaking of the next one, let's look at one. 9x squared plus 16y squared equals 144. Again, we need to solve for y. If you want to see if you can solve for y first, go ahead, pause and solve for y, and then come back. If not, we'll be doing this. Are you ready? So, subtract first. 16y squared equals 144 minus 9x squared. Divide by 16. 144 divides by 16 to get 9. The 9, however, does not, so we're just going to leave that as a fraction. Then square root both sides. Plus or minus 9 minus 9/16 x squared. And we can put this into the calculator and graph it. So, first step is we need to clear out what we have. So, we can start fresh. And now, to type in a plus or minus, we can use these squiggly brackets, which are second the parentheses, and do 1 comma negative 1. That'll multiply whatever we do by 1 and by negative 1. Now, technically we need parentheses after that to make sure we got everything, but the square root counts as parentheses. If we had an extra thing on the outside of the square root, we would need the parentheses for the function. Speaking of parentheses, notice 9/16 I put in parentheses, so I didn't accidentally do 9 divided by 16x squared. Then we graph it. And notice in this case they're both blue because it's the same function. It still has the gaps at the axis, but we can see that this one isn't quite a circle. It's been stretched a little bit. And we didn't have to zoom square because we're already zoom squared. So it's an ellipse. The center still at 0, 0. I would expect most of your centers to be at 0, 0 today. And then intercepts. Looks like we're at negative 4, 0, and 4, 0. And then 0, 3, and 0, negative 3. And so we have centers and intercepts. Moving on to another conic section. 5y squared equals x. We solve for y, so we can divide by 5. Square root both sides. Get y equals plus or minus the square root of x over 5. And we can graph it. So, go back into y equals. Hey, we already have this. We already have the square root. We just need to delete the stuff inside the square root and put x over 5. Makes it a bit easier. So x divided by 5, and we can graph. And we get that piece, the positive piece, and the negative piece. And so what does this look like? Well, there's only one of them, so it looks like a parabola. Now, a parabola doesn't have a center, but it does have a vertex at 0, 0. And then it opens. It can open 4 different directions. It can open up, down, right, or left. This one opens to the right. Let's look at another one. Now, if I were to take a guess, My guess is this one would be a hyperbola, purely by process of elimination. By the end of the chapter, you'll be able to look at these functions. I'm sorry, they're not functions. You'll be able to look at these equations and be able to tell what kind of conic section it'll be just by the equation. And that's actually not even very hard to do. But right now we're just graphing and playing around with it. So this one, we need to solve for y equals. So solve for y. So we subtract 9, and we can square root both sides. So y equals plus or minus the square root of x squared minus 9, which again is not x minus 3. It's the square root of x squared minus 9. And we can graph it. We go to y equals. We already have most of it. We just need to change the x over 5 to x squared minus 9. Sometimes it's easier just to delete everything inside. The x squared minus 9. And then we can graph it. And we'll get the positive one first. Coming there, and then over there. And then the negative one will come. This graph's in such a weird order. And over there, and that would be a hyperbola. Remember how I said that hyperbolas are a bit asymptotic? Can you kind of imagine the line? You can see a straight line here and a straight line here. Those will be the asymptotes, and we'll see those when we're working with hyperbolas. But this is a hyperbola. It does have a center. The center would be right in the middle, which 0, 0. Again, pretty much everything today, the center's at 0, 0. And it has vertices. That would be these points, just like where the parabolas would be. Looks like 0, 3, or 3, 0, and negative 3, 0. And it opens horizontally instead of vertically, because this could open vertically as well. And it would just be opening up and down. So that's how we would graph the different conics on the calculator, and they're all the same. We solve for y. We're going to end up with plus or minus square root, most likely. If we have to square root both sides, if we have a y squared, we will have plus or minus square root. And then we just graph in the calculator. Make sure that you have zoom squared. Otherwise, it's going to be all stretched horizontally because the windows are not square, even though the graphs were. We just see the shape. So the other thing we're going to do is we're going to use the distance and midpoint formulas. So using the distance and midpoint formulas, we start out with our generic points, x1, y1, x2, y2, and we'll use some actual points, 2, 4, and negative 4, 1, so that we can see what it looks like with actual numbers in it. The midpoint formula is just x1 plus x2 over 2, y1 plus y2 over 2. It's the average of the x's, comma, the average of the y's. You could also look to see, well, let's see, 2 and negative 4. What's halfway in between 2 and negative 4? If you think negative 1, you're right, and that's the midpoint for the x. You could do the same thing for the y. But here, well, what's halfway in between 4 and 1? All of a sudden it's a fraction. It's not quite as easy. And also, if the numbers are far apart, or if they're just ugly to begin with, what's halfway in between 3.7 and 13.1? Not so easy to think about. Add them together, divide by 2. So let's do that. 2 plus negative 4, divide by 2, and 4 plus 1, divide by 2. 2 plus negative 4 is just negative 2, 4 plus 1 is 5, divide them by 2. Negative 2 over 2 is negative 1, and I'd leave 5 halves as just 5 halves. You could say 2.5 if you really want to, but 5 halves is fine as well. And so that would be the midpoint between these 2 points. For the distance formula, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. I've never understood why the second one is before the first one. It doesn't matter which is our first point, which is our second point. It could be x1 minus x2. And honestly, the only difference between those two is whether it's positive or negative. When you square it, it's going to be positive. So unlike the slope formula, these two don't even have to be in the same order as these two. So it's really hard to mess up the distance formula. Just this minus this squared plus this minus this squared, add them together and square root. And the distance formula is really just a Pythagorean theorem. This is a distance of x's, the distance of y's equals the distance, the diagonal distance squared. We've just square rooted. Anyway, let's plug in our points. 2 minus negative 4 squared plus 4 minus 1 squared. 2 minus negative 4, well, that's a plus 4, so that'll be 6 squared plus 3 squared. 6 squared is 36, 3 squared is 9. Add them together to get square root of 45, which does simplify to 3 root 5. But with a lot of what we're going to be doing in this chapter, leaving it as square root of 45 isn't going to be bad, because the first step we're going to do is we're just going to square it, and you'd have 45. Yes, you can simplify it, you can reduce it, but not essential. So how are we going to use the dispoint and midpoint? The midpoint and distance formulas. Today we're going to be looking at circles specifically, and dealing with questions like find the center and radius of a circle that has a diameter with the given endpoints, and then we'll get 2 points. The center is going to be at the midpoint, so we can find the center. It's a midpoint formula. Just plug in our points. 3 plus 13 over 2, 6 plus 30 over 2. 3 plus 13 is 16, 6 plus 30 is 36. Divide each of them by 2, and you get 8, 18. There's the center of the circle with those endpoints of a diameter. And the radius, we're going to use the distance formula. We can use these 2 points if we want. We can plug it in. 13 minus 3 and 30 minus 6. I went that way just because it's easier to go 13 minus 3 than 3 minus 13. The bigger number minus the smaller number. So we get 10 squared and 24 squared. 10 squared is 100. 24 squared is 576. Add them together. We get square root of 676, which is 26. Now that is not the radius though, because these are the endpoints of the diameter. That would be the diameter. So if we know the diameter, how would we find the radius? Just divide it by 2. The radius equals 13. We could have also used the center with either of these 2 points, and that would have given us the radius. We wouldn't have had to divide by 2. But a lot of times, people just plug in the points they're given, and they get d equals 26, and they stop. Now remember, that's the diameter. You can divide by 2, or use the center, whichever works for you. So that's what we're doing. We're going to be identifying the conic sections, which are just cuts of a cone with a plane. Graphing them is how we're going to be identifying them for the most part. And that's graphing using a calculator. It'll have you sketch a drawing. Let's sketch a drawing. What does your graph look like? Show me on the paper. Don't just say graphed it. And then you'll be using distance and midpoint formulas to answer questions kind of like this. Anyway, hope you enjoyed an intro to conic sections, and I will see you in class.